This conference will now be recorded.
So very good evening, students. We were discussing various numerical problems on system of particles and rotational motion. So here so we had a little doubt or confusion in this particular problem, which I had already discussed in the previous class. So I'll clarify again this first, then we'll take up few more problems today and we'll conclude this chapter. Next day we'll start with gravitational motion. So let us read this problem first. So 7 identical circular planar discs, each of mass capital M and radius capital R, are welded symmetrically as shown in the figure. You can see here there are 7 discs, 6 are on the symmetrically situated from this middle one. Okay. The moment of inertia of the arrangement about the axis normal to the plane and passing through the point P. So this is actually the point P. As I was discussing in the previous class, this problem can be solved by using parallel axis theorem. First of all, you look this system, since it is symmetrically situated from this point O, this point O can be treated as center of mass for this system. Okay. Now look, if I take individual disk, suppose I take this disk, what is the moment of inertia about its own center, this center? That will be mr square by 2, right? So this will be the center of mass, sorry, moment of inertia about its own center of mass. So what about moment of inertia about this point O, or the center of mass of the whole system? So that can be found out using parallel axis theorem. This is the moment of inertia about this center of mass, and this will be m into r square, that is 2r here. You can see here m d square. This is 2r square. So this will be moment of inertia of this particular disk about this O. So I have 6 such disk. This is 1, this is 2, this is 3, like that. It is 6. Suppose this is 5, this is 4. So there are 6 disks like that. So I can multiply 6 with this to get the moment of inertia of each of them with this center of mass. Okay, I hope you are understanding. So let me show you that we have to find out moment of inertia about P point. Look this P point. If I can calculate the moment of inertia about this point O for the whole system, then I can use this particular parallel axis theorem, where D will be actually 3R. It is R, this is 2R, 3R, and it is symmetrically situated. Okay, so this is symmetric about all of them. If I just yeah, so that will give you the answer. Okay, so first of all, what is moment of inertia about O? So that will be moment of inertia of this particular disk, first of all. So this is actually mr square by 2. Okay, mr square by 2, sorry, mr square by 2. Then 6 into mr square by 2 plus see 6 into, I'm just writing the second contribution, that is the, so this is the moment of inertia of this particular disk about this O. This is fine. And I was calculating moment of inertia for all 6. See about this O. So this will be having m r square by 2 plus 6, sorry, plus m 2r whole square. Okay. So this, let us just calculate. So this is m r square by 2 plus 4 m r square. Okay, so this will be 9 m r square by 2 into, okay, so this is for 1, this is for 1 about this O. Okay, so there will be such 6 of that. So this will give you, right? I hope you are agreeing with me. What I have done, I have just calculated moment of inertia of the center one, that is m r square by 2 about this, its own, like about O, about an axis passing through O, and I am calculating moment of inertia of all 6 disks about an axis passing through O. Okay, so see, this is the moment of inertia for a particular, for just one. This is the moment of inertia, suppose for this m r square by 2 plus parallel axis theorem, m d square d is actually 2r. From here it is r, another it is r, 2r. So this is how I get 9 m r square by 2, and I have to multiply 6 to get the moment of inertia for whole system about O. I hope you are agreeing me. Okay, so I have got how much? We have got, see, 9 into 6, 44, and this will be 1. So 55 m r square by 2. So this is the moment of inertia of the whole system about this, about this center, about the center. Okay, then look, I have got kind of, see, I have got moment of inertia of the whole system about this. Okay, now look, if I calculate moment of inertia about a point, sorry, axis, about an axis, kind of this, actually you can just think of this. So from the center, the distance of this point P, 1r, see, for this particular disk, suppose, okay, for this particular disk, see, from the center, actually you should not be thinking for this particular disk, it is for the whole system. So you have, this is 3r, okay, and this is the axis which is perpendicular to the plane, and it is diameter, you can think of a kind of diameter which is perpendicular to the plane of this disk. So you can use this is the moment of inertia, we have got IO plus md square, where d will be actually 3r. Okay, and that is for one, that is for one of this disk. Okay, that is for one of this disk. I have actually 7 of them. Okay, 7 of them. So therefore this IP, moment of inertia, will be IO plus 7 of this disk into m3r square. Okay, so this is 5 by 2 mr square plus 63 mr square. So this will give you 55 plus 6, and this is 12 by 2 mr square. So if we add them up, 181 by 2 mr square. Okay, so you look, this will be the answer. Okay, the first option will be the answer for this question. Okay, so this is how we have to solve this problem. Okay, we'll move on to the next problem. So here second problem says a string is wound around a hollow cylinder of mass 5 kg. Look, this is suppose that do that, right? We open, do that. Suppose a wire, so it has, suppose, a radius. Radius is 0.5, so capital R, let us say this is capital R radius, and there is like this, it is wound. Okay, and there is a force given here, 40 Newton, with which this cylinder is actually pulled. Now the string is pulled with horizontal force 40 Newton, and the cylinder is rolled with slipping. Cylinder is rolling, sorry, is rolling without slipping on a horizontal surface, as you see in the figure. Okay, so this is the thing happening here. Now what will be the angular acceleration of the cylinder? Neglect the mass and thickness of the string. Okay, so here look, when actually if you see condition for, see here options are there, 10 radian per second square, 16 radian per second square, 20 radian per second square, and 12 radians per second square. So the condition for rolling without slipping, you should be understanding about this. Without slipping, you should understand this condition first. Okay, what is the condition? The condition is that for this kind of motion, v is equal to r omega, sorry, linear velocity and angular velocity will have, angular velocity and linear velocity of this center of mass will have a relationship, v is equal to r omega. Similarly, the acceleration will be, sorry, acceleration a will be r alpha. This is one point. Another point is that each time the point of contact will be at rest. This point will be at rest. Okay, at rest. So we can think of one thing, that in case of rolling motion, there will be a torque acting about this particular point. Okay, about this particular point, there will be a torque acting about this particular point. See, at this fixed point, we can actually, this is called the bottommost point. So we can actually, for bottommost point, for bottom most point, we can write that the torque, let us say this point is B, torque at B will be is equal to I alpha. Okay, we can calculate the torque about this point, and from there actually you will get the alpha value. Okay, so what is torque? What is the torque? Torque is actually force time the radius of this cylinder. So here what is the, so I can write F into R is equal to I alpha, where I will be moment of inertia of this cylinder about, this is a hollow cylinder, first of all. So hollow cylinder, moment of inertia about the diameter. For a hollow cylinder, moment of inertia about its own axis is mr square alone. Okay, mr square about its own axis. Okay, then what about this? This is distance r, capital R, radius. So moment of inertia about this particular B point, like axis passing through this B, that is the diameter. So that will be equal to mr square. This is the moment of inertia about its own axis or center of mass through center of mass, plus mr square. Mr square. Why? Because this is the distance r. Okay. So this is moment of inertia. So it will be actually 2mr square. I hope you have understood this. The moment of inertia about this point B I'm calculating, that is actually mr square about the center of mass plus mr square or md square, that is the distance into a distance square into mass. So we can write this as 2mr square. So we actually have to find out alpha. So how do you calculate alpha here? F into r divided by I means 2mr square. Okay, that means F by 2mr. Okay, now if we put the values of this, F is equal to how much? 40 Newton. F is equal to 40 Newton. Okay, 2 mass is 5 kg and this is 0.5. Okay, so this will give you this 10 515 goes off. So this is giving us, okay, I have F into R. F is actually 40 Newton. I think things are all right. Let me check once again. Torque. This is the radius. Oh, I am sorry. We have to actually take this. We have to take this distance. So it will be 2R, not R. 2 into F into R. I'm sorry. So this will be 2 into F into R. So 2 goes off. Okay. So this 2 will not be there. So okay, I'll just rewrite the force into, okay, this was all right. Okay, so this is 2R. Okay, that is what we have to write. So torque is equal to I alpha, and see this torque is force into the distance between them, F into 2R, is equal to I is 2mr square, we have seen already, into alpha, which we have to calculate. So 2 goes off. So alpha is F into R divided by mr square. So R goes off. So 40 divided by R means 0.5 and M means 5 kg. Okay. So this would give you how much? This will give you 80. So this will be 16 rad per second square. Okay. This would give you 16 radians per second square. Okay, now similar, almost similar question here. A homogeneous solid cylindrical roller of radius capital R and mass capital M is pulled on a cricket pitch by horizontal force, assuming without slipping, assuming rolling without slipping, angular acceleration of the cylinder. So similar questions almost. We have already solved one. We'll be able to solve this also. Okay. So this is similar to the one we have done. For pure rolling, we know for pure rolling, we can write, we have tau is equal to I alpha, as I was saying you. Okay, so what will be the alpha? Alpha will be tau, that is the torque divided by moment of inertia. So torque will be how much? So torque will be, for in this case actually, uh, a solid roller of radius r and mass m pulled by horizontal force, okay, without slipping, what will be the angular acceleration? So in this case, similarly we can write F into R is equal to, see, this force actually, we are just considering the force is applied. Because since it is not given here, we are just considering the force about the center of mass, okay, about the center of mass and about this point. Okay, that's why we have taken R. Since it is not mentioned, the horizontal force in case of road roller, if you look, the force is given at the center of mass itself. Okay, horizontal force is given at the center of mass for the road roller or for a roller. So that's why we have taken this as, so the force is given at this center of mass. That's why we have taken F into R for the torque. It is not similar to this one. It is similar, but here the force was given at the periphery, not at the center of mass. Okay, that's why. So F into R, this will be equal to I alpha. I is the moment of inertia of the cylinder, and this cylinder is actually a solid cylinder. So solid cylinder will have moment of inertia m by 2 r square, plus we have to do m r square about the diameter, right? So that's why it will be 3 by 2 m r square. Okay, so we have I, so this is Fr is the torque and I is actually 3 by 2 m r square. Okay, so we can just put it here. You can put this as F into R divided by, so 2 will be in the numerator, 3 m r square. Now, so this will be 2f by 3 m r. Okay, so this is the answer. I'm just removing all this. Okay, so this is the angular acceleration. Alpha is equal to 2f by 3 m r. This is the answer, and you can see the option D will be the correct answer for this question. Okay, now we'll move on to the next problem again. Okay, so this is an interesting problem. Look, we'll read the problem first. Two coaxial dishes. Okay, two coaxial dishes. This is one. Suppose this is another one. Coaxial dishes. One has moment of inertia 2I1 and another one has I1. Okay, rotating with respective angular velocities. What are those? Suppose this has omega 2 omega 1 and this has only omega 1 angular velocity. Okay, angular velocity while rotating about this axis of their symmetry or passing through their center of mass. They are brought in contact, then they are brought in contact with each other, and thereafter they rotate with a common angular velocity. Okay, when they brought in contact, they rotate about a common angular velocity, suppose omega prime. Then what if this EF and EI with the final and initial, this is the final kinetic energy, total energy, and this is initial total energy, then what will be the value of EF minus EI? That is the question you have to solve. You have to find out the EF minus EI. Okay, what is the difference between the total energy? That you have to find out. I'll just provide you the options first. What are the options given over here? The options given over here is I1 omega 1 square divided by 24. Then further it has option C. Option C is 3 by 8 I1 omega 1 square, and D I1 omega 1 square by 6. So these are the options given. So look here, what are the informations given? Initial, they have actually fixed moment of inertia I1 and I2, that is fine. So and then they had their velocities, angular velocities omega 1 and omega 2 omega 1 about their common axis. When they are brought in contact to each other, then their moment of inertia, angular velocity changes. Suppose that is omega prime. Then what is the value of EF minus EI? That means this is the final total energy and this is the initial total energy of the system. You have to find out the difference between them. Okay, now see, we can use the using conservation of angular momentum, conservation of, so Using the conservation, the law of conservation, we get I1 omega 1 plus I2 omega 1 will be equal to I prime 1 omega prime, sorry, I1 will be the same, I2 plus omega prime. Okay, so this is from conservation, law of conservation. And see what are the omega 1. See, I1 is given as, suppose let us take that as I, and I2 is given as 2I. Okay, I can take I1 is I1 itself and I2 is 2I1. So from here I can write I1 omega 1 plus 2I1, I'm sorry, I think I1, and the other one has moment of inertia I1 by 2. And here also omega angular velocities, initially they don't have the same angular velocity, they had different angular velocities, omega 1 and omega 1 by 2. So this one, okay, let me just write omega 1 angular velocity, another angular velocity was omega 1 by 2. This is what was there. Okay, so I can write omega 2 here. So it is, look here, I'll get two equations. I2 omega 1 by 2, I2 again I1 by 2, and here also I1 and I1 by 2 omega prime. We can find out omega prime over here. So this is actually 4. So 5 I1 omega 1 by 4, 3 by 2. So 2 goes off here. So omega prime will be actually 5 by 6. This I1 will cancel each other. This will be 5 omega 1. Omega prime will be 5 by 6 omega 1. Okay, I have got this omega prime. Now we'll see the kinetic energies. See, final kinetic energy will be half I1 omega 1 square, sorry, omega prime square plus half I2 omega prime square, where I2 we know half I1 omega prime square is 5 by 6. Let us omega 2 is I1 by 2, 5 by 6 omega. Okay, so in this case half I means I1 by 2, I1 by 2. So this will actually give you 25 by 72, along with that omega square will be there, plus this is 25 by 84. Now if you add this two, you'll get the EF. Okay, anyway 25 will be common, I1 will be common, so 25 I1 divided by, you will get, okay, so 72, we can just get a common factor. Okay, so I'll just write the answer what we get for this thing. EF value will get actually 25 by 25 by omega square, or omega 1 square, right? So it will be actually 25 by 48 1 by 4. This is 1 by 4 into this, 4 into 36, and this will be 2 into 36. Okay, so 2, if we take common, 2 and 4 actually, okay, so look what will be happening here. 36 common, 1 by 2 plus 1 by 4, this is the thing. So this will give you 2 plus 1 divided by 4. So 25 into 3 by 36 into 4, this will be 12, so it will be 48. Okay, so final moment of inertia, sorry, final kinetic energy we can find out. So that is this one. I'm just writing somewhere here, the 25 by 48 I1 omega square, okay, or omega 1 square. Okay, now what was the initial so initial kinetic energy will be, so total energy will be half I1 omega 1 square, and then half I2 omega 2 square. So this we know, one by 4, this is I1. Okay, so from here we can find out 3 by 4. Sorry, this is omega 2 means there is omega by 2, right? Omega by 2, omega square by 4, so this will be 8 actually. 4 for 16, sorry, 16. Okay, so actually if we calculate it for the initial part, okay, let me just do it. Just quickly I'll solve the numerical part. Okay, let me just write it, then it will be all right. I2 is I1 by 2 into omega 2. Omega 2 is actually omega 1 by 2 again square. So this is half I then it will be 9 by 16 I1 omega 1. Okay, so then you can find out the difference, EF minus EY. Okay, so EF minus EI will be 25 by 40 minus 19 by 16 along with this factor. Then this is 27. So here it will be minus 3. 3 by, so 3 by 48. This will be actually, okay, let me just go to the next page somewhere and do the calculation part in cool brain, then it will be easier to solve. 9 by 16, 25. So this will be 2 actually, okay, so minus 2 by 48. Okay, so here this difference will be actually, this will be 2 by, so the answer will be, let me clean everything. The answer will be the option A, that was actually minus 5 by, sorry, the correct answer will be so I1 omega 1 square into minus I1 by 4. Okay, so this is the answer for this particular question, coaxial dishes. Now we'll actually take up one more quick problem and then we'll conclude. So this problem is little lengthy, but we will solve it for our understanding purpose. So this question states that a horizontal disk rotating freely, there is no options here because this I have taken from not from exactly JE paper but some other paper. This will help you to actually solve many problems related to this kind of questions. So that's why I'm just interested to discuss. Here, a horizontal disk rotating freely about vertical axis. So there is suppose a disk like this. Okay, it is rotating about this vertical axis and makes 90 revolution. Let us say this is initial revolution per minute means this is kind of frequency we can find out. See, frequency, initial frequency we can find out 90 revolutions per second. If we can make it 90 revolutions per second, this is per minute, so it will be divided by this, will give you revolution per second, which is actually a frequency, initial frequency. So initially the frequency of the rotation was like that. Okay, a small piece of wax, a small piece of wax falls on vertically on the disk and stick to it at a distance. See, this is a wax just fall on the disk at a distance smaller from the axis of rotation, and it is getting stick. It has got stick to the disk. Now, if the number of revolutions per minute reduces because of this wax stick with this disk, rotating disk, now the frequency changes. It suppose this is final or F, right, F1 and F2. F2 is becoming revolutions per minute, 60 revolutions per minute divided by 60, so it will be 9/6, and another one is actually 60, that then it is actually 1 rps. Okay, 1 rps. Okay, one is see, that was 90 revolutions per second, so it will be we can just further simplify 3 2, so 1.5 rps. This is 1.5 and this is 1 rps f2. Then that means the frequency actually decrease. Then moment of inertia of the disk you have to find out. So how to calculate moment of inertia? Here actually we will be using conservation of law of conservation, law of conservation, conservation of law of conservation of angular momentum. Momentum. We know the angular momentum L is equal to I omega. I is moment of inertia and omega is angular frequency. So we can write 2 pi f into I. So L is equal to 2 pi f into I, we can write, isn't it? So angular momentum is conserved even though this particular mass has dropped. So suppose initial angular momentum was L1 and final is L2. These two are actually always, these are equal to each other. That means you know omega 1 I1 will be equal to I2 omega 2. Okay, this is the formula. From here we can find out the moment of inertia. Okay, so what will be the moment of inertia of the disk about the given axis, and so let us suppose the moment of inertia of the given axis is I. Okay, let us say suppose moment of inertia MOI of the disk about the given axis. Given axis is I, and moment of inertia of the disk becomes and I2 be the moment of inertia when wax falls and stick to it. Okay. So this I2 moment of inertia, see I2 is the moment of inertia when this mass has been sticked at r distance, small r distance. Actually, this small r distance has to be written. See this. Okay, since there are values at r distance from the center of mass. This r will take us some distance. It is centimeter, some 8 centimeter. Let us say. Okay, or some value will take it. Okay, so you can see the moment of inertia changed to I2 when this is sticked here. So this I2 can be written as ICM, or its own moment of inertia plus the m small r square, right? This I cm is nothing but I itself, moment of inertia of the disk about its own axis. Okay, now I can write I1 omega 1 is equal to I2 omega 2. Okay, so I1 initially it was I. What is omega 1? Omega 1 is now RPS, 1 RPS, and there is 1.5 into 2 pi, again it will be multiplied. 2 pi multiplied with 1.5. Okay, and this is I plus mr square whole into omega 2 means 2 pi into 1. Okay, now if we simplify, what we get, see here it is 1.5 minus 1, I is equal to mr square. Okay, m into r square. Okay, so it will be 0.5 I into mr square. Okay, then I will be mr square by 0.5, so this will be 10 divided by 5 mr square. That means it's 2 mr square, 2 into mr square. If suppose in this problem actually piece of wax of mass m, small m is there, and the distance r is given, so mass and distance are not given, so I'm not going to calculate the value, but you look in this way you have to solve the problem. What we have done, I'll just recap what we have done. So we have supposed that the moment of inertia of the disk about its own axis to be I, and when the wax has been stick to a distance r, on this disk, then its moment of inertia got changed, and that is I2, suppose. And that I2 can be found out by using parallel access theorem. So I2 is equal to I plus mr square. Okay, mr square. Now we have got I2, I1 we know, that is I, and omega 1 was given, and omega 2 also was given. Okay, so rps 1.5 rps into 2 pi will be the initial angular velocity or angular frequency, and I2 is, we know, I2 is this one, I plus mr square, and along with that 2 pi into 1 rps, which is reduced by 0.5. So upon solving, we get I is equal to 2 mr square, 2 into m into small r square. Okay, so the answer, look, the answer for this question will be the moment of inertia. Therefore, moment of inertia of the disk is given by 2 m r square. Okay, this is the I2. Okay, sorry, not I2, the original moment of inertia I, 2 m r square. Okay, so this is how you have to calculate problems like this. So this problem is given in this way, but sometime it will be given like there is a rotating disk and there is an ant or an insect just was there on the periphery, and it starts walking towards the center. Then at certain distance, when it reaches at certain distance, what will be the angular velocity? If the moment of inertia are given, then you will be able to find out. Okay, what will be the angular acceleration, angular velocity, or what will be the moment of inertia of the disk itself? This kind of questions will come from this particular problem. Okay, so you have to use the conservation law of conservation of angular momentum. Okay, so with this we'll stop it here for today. Next day we'll start with the gravitation chapter, revision of gravitation. Thank you for your patience. Bye for today.